Hello, it's Keith here, and this is lesson 70 of the platform-specific series of my Z80 assembly programming tutorials. Now, today we're going to be looking at sound for the second time on the Sega Master System and also the Game Gear, because they're basically the same system. Now, what we're going to be doing today is we're going to be writing something called ChibiSound Pro. Now, this is a platform-specific driver that I've written on a wide variety of different systems, not just on the Z80, but also 6502 and 68000. And what it's designed to do is it plays sound on that underlying hardware in a compatible way. It's basically a hardware abstraction layer that will allow us to make sounds in the same way in all the systems. And what we're going to do with this is we're going to use it for playing music. So I've got a multi-platform music player called ChibiTracks, which will play simple music files on every system in the same way. So we can write one binary music file that is, sorry, and then that will play on all of the systems in something comparable in the same way. Obviously the hardware is going to work differently, so it won't sound exactly the same, but it will have the same kind of feeling to it on every system. Now, the driver that we're going to write will take a total of 4 bytes of data. Now, the first byte is going to be in the H register, and this bit 0 to 6 will be the channel number, so 0 to 127. Although, in effect, we're actually only trying to aim for 3 channels. Where the original system I wrote this for was the AOY, which had 3 channels, so that's what my music player uses, but in theory, 127. The top bit will be the noise on-off bit, so that will define if we're enabling noise for that channel. We have a 1 byte volume from 0 to 255 with 0 being silent, and we have a pitch in DE, so that's a 16-bit value from 0 to 65535 with 0 being the lowest pitch, 65535 being the highest. And while that's going to be true on every system, we're not trying to match those numbers, so the pitch 32768 will be the middle range of the pitches the hardware is capable of, but it won't be the same note on every system. Now, to play a note that matches on every system, we will have a lookup table. So we'll have a look at that lookup table later. Now, the Sega Master System and the Game Gear, they have the same sound hardware, and this is a relatively simple piece of hardware. The PSG basically takes a single byte that we write to port 7F, and the bits within that byte will define what we're actually trying to do. So in a sort of template style, not entirely always the case, but basically the top bit is the latch bit. Now this will be 1 for the first byte of data, but for the tone there are 2 bytes, and the second byte will have a 0 there. The next 2 bits are the channel in most cases, and then the remaining 4 bits are the actual data. So we will send the tone with that format for the low part, the low nibble, and then we will send a 6-bit high near byte with the latch bit set to 0, and that doesn't match that format, but everything else does. We have a volume, this will be set with this format here, and the volume is 4 bits there. And we also have a noise channel, and this is rather a special channel, and we can set that with the top bit set to 1 and the tone set to 0 here. And this can either basically just use a 2-bit frequency, or we can link that to tone channel 2, and tone channel 2's frequency can be used for our noise. Now let's go over to our source code and let's actually hear this in action so that we can actually get some idea of what we're going to end up creating. So the first thing we're going to use is we are going to use ChibiSound Pro Test here. This is a very simple testing routine that I used to test the frequencies. Now you can hear we've got a very high frequency there. And as I change the number down there using the simulated joystick here, you can hear the pitch goes down. And if I press the fire button, you can hear we've got noise. Now, if I'm moving the frequency there with the noise enabled, and you'll hear we've only got a very simple noise there, and that's because we're using the 2-bit option there. The alternative is we link to tone channel 2, which will reduce the number of tone channels we have, but this will mean that we have better quality noise. Now if I just run this again, you can now hear that we've got a wide range of frequencies of noise there. And so that is the difference between the so-called simple noise and the linking to tone channel 2. Now the whole purpose of this is to allow us to play music, and so what I've got here is the ChibiTracks software playing the binary output of the Chibi Actors theme. I converted this. It was originally written for Arcos Tracker. I converted it to my ChibiTracks Pro, and this was for the CPC originally for a demo, but it plays on every other system as well, including this one. that's what we're sort of aiming to achieve there, playing music on lots of different systems with the same binary file. Now, to achieve this, we have this driver called ChibiSound Pro, and this is the Master System version, and this is what we're going to be looking at in today's lesson. So basically, the first thing we've got here is an octave. This is a lookup table of the various values for D and D, for the DE pair, which is what we will want to send to the set command to set a frequency. So we've got the various notes of the octave here, and this is something we would look up for when we want to play a note. So if we wanted to play C, we would look up one of the values in that column there. Now, if we want a C sharp or a B flat or something, we basically take two values, add them together and divide by 2. That is how you calculate the correct tone for the sharps and the flats. So we've only got what I would call the pure tones here, not the sharps and the flats in that table, and that does work okay. Now, we do have a few other things that we're going to have to do. As I say, the definition that I created for the ChibiSound Pro drivers needed to support a channel number from 0 to 127. However, what they do with later channels is up to them. The only thing is that the lower numbers are higher priority, so you could ignore every channel over channel 0, but you should process at least channel 0. Now, what I do in this case is I basically wrap around, so it would be every 4 channels, and I've got a lookup table for the bits for the various channels there, and so channel 3 there, if 0, 1, 2 and 3, channel 3 there is going back to channel 0. Now, those are the bits for the CC section of the parameters we will want to send. So that's how I'm dealing with the fact that we might be asked to use channels that don't exist on this hardware. So I'm going to use that. Now, the other problem we've got is however we deal with noise, we've only got one noise channel. But the ChibiSound Pro driver intends to be able to set noise on or off for each of the channels. And so what we're actually going to do is, when we're asked to turn on the noise on channel 0 or channel 1 or whatever, we're going to remap that all to channel 3, which is the dedicated noise channel. And we're going to have a virtual noise channel on all the other channels that is going to be marked as on or off. And so if noise is turned on channel 0, but then later it's turned off, we're going to redirect that all to channel 3. And we're going to use these bytes here to detect when the noise has been turned off again, and then turn off channel 3 when the noise is actually turned off. So that's how we're going to deal with the noise issue as well. Now, this has 2 different versions of the noise. There's a simple noise, which just uses the 2-bit noise rate there, or there is complex noise, which will turn on the use tone 2 option, which is done by setting those 2 bits. And then we're going to remap the frequency to tone channel 2, turning off tone channels to actual tone. So that's how we're going to do the advanced noise. Now, when ChibiSound Pro set is executed by whatever he's calling it, either my music software or something else, the H register will be the volume, 0 to 255, L will be the channel number, and the top bit will be the noise, and DE will be the pitch. So the first thing we're going to do here is we are going to use the channel mask, and we are going to basically convert that 0 to 127 value to a 2-bit mask here for 0, 1 or 2. 3 would be the noise channel, so we're not using that. So that's what we're doing here. We're reading in an entry from that lookup table, and we're basically setting B to a valid channel mask there. Now, the next thing we're doing here is we're checking if the noise is on. Now, if the noise is on, we're going to jump to this label here. If the noise is off, though, what we want to do next is we want to check the entry for this channel within that noise virtual table here. And we're checking to see if the noise was on and now is off. If that's the case, we now want to turn it off. And the way we do that is we set the volume of channel 3, which is the noise channel, to silence. Now, basically 4 1 bits here is actually silence on this system. So what we're basically doing here is we're setting channel 3, the noise channel, to volume 15, which is silent. And so that is turning off the channel. And all of the rights are to port 7F on this system, which does whatever the respective bits ask it to do. So that is silencing the sound there. Now, if the noise is now on, then we're going to have to deal with that. So the first thing we're doing here is we are silencing the matching tone channel, because if we've been asked to turn the noise on channel 1, we actually don't want the tone to play on channel 1. So we're silencing that here. So we're ORing in the 2-bit mask for the current channel, those 2 C bits there, and we're setting the volume to 15, which, as I say, is silent on this system. So those 15 is the quietest. So that's silencing the tone channel. And then what we're going to do is we are going to set the noise in the virtual lookup table, channel noise there, and that's marking this as on so that we know later when we want to turn it off again. Now what we do next depends on if we're using simple noise or not. If we're using simple noise, then basically we can only use a frequency rate of 0, 1 or 2. And so what we're doing here is we're taking the top 2 bits of D here, and we're basically limiting them to 0, 1 or 2, and we're going to then position that into the bottom 2 bits here. And that's because this is the rate for the noise channel setting here. So the channel bits are set to 1 there. The T bit there is set to 0, the type bit, and then we're setting the rate there. And so that's what we're doing here. We're setting the rate of the simple noise. The only other thing we then need to do is we need to set the volume. So we're taking the top 4 bits of H here. We're XORing those because the loudest value that we passed in H would be 255, but the loudest value on this system would be 0. So those bottom 4 bits we want to be 0, but we want the other bits all to actually be 1 anyway, because we want to set the volume of channel 3, in this case the noise channel. So that's what we're doing there, and in that case with simple noise we would actually be done. But if we're not using simple noise, what we want to do is we want to do a couple of things. The first thing we want to do is we want to redirect the later commands to channel 2, because channel 2 is going to set our frequency rate there. So that's why we're setting B with these 2 bits set to 1, 0, because that's selecting channel 2 later on. What we're then doing is we're then silencing channel 2's tone, because we don't want to hear channel 2, we just want to use it for noise. What we're then doing here is we are setting the noise frequency, and we're setting the 2 R bits, the bottom 2 bits, to the value 3 here, and that's because the rate value 3 means use tone 2. It's not actually a frequency for the noise. So that's what we're doing there. The other thing we're doing on this system is we're then shifting D and E by a few bits here. We're basically restricting the range to the C000 to FFFF range, because basically anything lower than that was very, very low noise, basically silenced. So they weren't viable frequencies for noise, but they are viable frequencies for the tone. So we're correcting the noise frequencies there for the following code. Now the following code is run for the advanced noise or for regular tones. So the first thing we're doing here is we're flipping the bits of the DE pair here, and we're going to use this, and this is because the frequencies are reversed, so a very low number for the sound hardware is a very high pitch, and that's the opposite of what I wanted to use. So that's what we're doing there, and then basically what we're doing next is we're shifting the 16-bit value into this position here, into a 10-bit value, because that's what this system wants. It wants a 6-bit part and then a 4-bit part, and so we're shifting those accordingly. We're then shifting the low part so that the bits are at the bottom. We're then ORing in with the top bit set to 1 and the channel number in B there. Basically these 4 bits here are the frequency in this format here with the channel ORed in, and we're sending that to the hardware, so that has set the low byte of the frequency. Now the first byte of the frequency is set with the latch bit, the top bit as 1. The second byte is set with the latch bit as 0, and then the 6 bits there are the frequency, and so that's what we're sending here. We're loading in D here, and that is in that format there. So that's the high part of the frequency. Now that's what we're doing there, but there is one more thing we need to do, and that's to set the volume. Now if we're setting the volume of a regular channel, we just do that, but if we're setting the volume of the noise channel with advanced noise on, we need to redirect this to channel 3, because we set B before to channel 2 so that we would set the tone frequency with this code here, but we now need to set the volume of channel 3, and so in that case we are basically redirecting the volume part to channel 3 again. Now setting the volume is pretty straightforward. Basically we're taking our H byte here, we're shifting the bits to the right because we only want 4 bits here. This is all we want. We're then XORing those 4 bits because again the volume 0 is the loudest on this hardware. We are setting the type bit to 1 here, that's this bit here, that's that one there. We're setting the latch bit to 1 here, and we're ORing in the channel number into these 2 bits here, which is setting the volume for that channel. B is of course the channel number there. Then we're sending that to port 7F, and that's all we need to do to create the sound for this hardware. So there we go. Now, as I was saying, you can go to my website, download the build scripts, and you can have a go with this yourself. And you, as I would say, you're welcome to use the source code in any way you can in your own projects, even if they're commercial. You're welcome to do so. If you're interested in seeing more work done on the Chibi Tracker software for Windows, or more work on this ChibiSound Pro thing, please consider backing me on Patreon, because it's the only way I can justify keeping working on such complex topics. The reason I wrote this software originally is I was thinking of writing games on multiple platforms, multiple systems, but I simply don't have the time writing the tutorials. So I've actually written a piece of software here I no longer have any use for. So the only reason I'm going to continue doing that is if people are interested in it and are willing to financially back me, because it's something I have no use for myself. Anyway, I hope you enjoyed what you've seen today. Thanks for watching, and goodbye.